director here at the Kavli Institute for Theoretical Physics at UC Santa Barbara, and I really wanted to join just at the very beginning of this wonderful occasion to say a little bit about the origin of the collaboration we have between the KITP and the National Society of Black Physicists. It started before the pandemic in discussions with Lisa Stewart, who's here, and Stephon, when he was then president of the NSBP, about ways in which we could collaborate more. And out of those discussions arose this seminar series, which we're happy to be hosting now and into the indefinite future. Everybody still is willing to come on Zoom, but it really has been a great collaboration for us, and I hope for all of you in NSBP. And I also just wanted to really say how great it was with Stephon in helping us as well create a program here called KITP Fellows, which is now supported by the Heising-Simons Foundation, that provides opportunity for faculty who are at non-R1 minority serving institutions to come here and be here for extended periods. And that proposal and that successful program that we've just started really came out of discussions with Stephon and others at NSBP, including many chairs at HBCUs, which were very clarifying for us on ways we can engage. So I want to thank Stephon for that, and hope to see you next time I'm in New York, and I'm going to hand it over to Elon for the introduction.
Okay, hello everybody, happy Thursday. Thank you so much, Dr. Bilson, for opening up the session today and for coming here to continue supporting this effort. I'm going to go ahead and give some context here. So my name is Elon Price. I'm a second-year physics PhD student at Auburn University in Auburn, Alabama. And I also serve on the NSBP board as the student representative. This means that I work closely with the Student Council, which we are 11 members strong, and one of our members, well, actually multiple of our members are here with us today. But one of our members, Carlton Smith, will be serving as our Q&A moderator today. So with that, I would like to start this introduction by giving some context about Professor Alexander and how I've come to know him. So I always describe him, and I just described him to Lisa, as the idea machine. You know, the first time meeting this man, I knew for a fact that he had so many really interesting ideas, and he was just very, very highly intelligent. And he served as a really important role model for me, because the first time I actually heard his name was in a YouTube video where he was explaining the relationship between physics and jazz. So Professor Alexander actually served as the second Black physicist that I ever knew of, aside from, of course, Neil deGrasse Tyson. So, and this was in my third physics class that I took in undergrad. So he was the second Black physicist that I heard of. And I also found out that he was a fellow Caribbean hailing from the island of Trinidad. And he was just such an intelligent and talented individual. And I appreciated how he talked about the intersection of music and culture and physics, because I think that's really important in our community at NSBP. So I have to say that as far as the Student Council goes, Professor Alexander has had an integral role in creating our Student Council community. So this was a time where we had 3 members, we expanded to 11 of the old council, and we were all restricted to Zoom. You guys know this. And so he really encouraged us to create a community, even though we couldn't meet in person, and to continue communicating together and supporting each other. And we did that, but he was also there at all of the council meetings supporting us as well. So I really have to thank him for that. And I also have to thank him for connecting me with the Event Horizon Telescope collaboration, which eventually led to me defending my master's thesis. And here I just wanted to share a picture of us meeting for the first time as the Student Council in New York City. And of course, Dr. Alexander was there supporting us that time as well. And we had a blast. We didn't realize how close we had grown, even through Zoom, over the year that we were working together. So with that, I would like to give a little bit of educational background to Dr. Alexander. So he is a theoretical physicist, as you probably may have known, but more like a cosmologist, and he specializes in particle physics and quantum gravity. So this involves string theory and loop quantum gravity. He received his bachelor's from Harvard College in 1993 and his doctorate from Brown University in 2000, where he's currently a professor at. He's had postdoctoral fellowships at Imperial College, London, and Stanford and SLAC, which is the Stanford University Linear Accelerator Center. He's held faculty positions at Penn State, Harvard College, and Dartmouth as well. As you may know, he studies the interconnections between music, physics, mathematics, and technology through recordings, performance, teaching, and public lectures like the kind he's giving today. Has an extensive career as a musician and performed and collaborated with Will Calhoun, Brian Eno, Mark Carey, Vernon Reed, Ronnie Barrage, and Jared Lanier, to name a few. So with that long and official introduction, I hope I did it justice. I would like to formally welcome Dr. Stephon Alexander as our Innovate seminar speakers today.
Well, I don't know. I mean, first of all, I want to thank Lars Bilsden, the director of Kavli. I want to especially thank Lisa Stewart and the Kavli Institute for their, back in the days, when we were in the middle of the pandemic and things were rough, the Kavli Institute, through Lisa Stewart ship and Lars' support, we were able to build out this beautiful Innovate seminar series. And who thought the day would come where I would be invited to engage y'all? That's the first thing. But secondly, I would say, there's no greater joy to see the students, to see, Elon, who I met 3 years ago when she was undergraduate, to see Carlton now, who's starting his PhD program at Yale, who was a Simons NSVP scholar, just to see you all grow. There's no greater joy in terms of the work that we do. And I'm sure Lisa and Lars can agree with this. This is where, I think this is what we're about. We're about, really making sure that we can pass it on to the next generation and you all could, solve and address the problems that we're going to pass on. And on that note, I hope to see many of you at the upcoming NSVP, our first in-person conference in Charlottesville. And I want to thank the National Society of Black Physicists for their continued support, our resilience, and that we are keeping our eyes on the ball, trying to promote the success and the excellence of Black physicists and our friends. So on that note, let's begin the talk. I doubt that I will be able to get all of my talk completed because, and that's okay. I think what I'll just do is do as much as I could, and we'll call it a day. Okay. So let's just begin. And I think what I need to do now is start this talk, and let me now go to the beginning of this talk. Okay. So the title of my talk is the Chiral Universe, and let's begin. First of all, I want to give credit to my students, past and present. My recent past PhD student is now Dr. Leah Jenks, who is now a postdoc at the University of Chicago at the KICP. Michael Toomey, who's finishing up this year, and so you should hire him. Tats Daniel, who joined us recently from MIT, he's in his third year. Alejandra Roseli Calderon, who's now at UC Santa Cruz. And my new student, who joined actually from UC Berkeley as an undergraduate, Lawrence Edmonds. So a lot of this work is based on the hard work done by my students and myself and my postdocs. So let's begin with 3 mysteries. So I'm going to kind of orient my talk around these 3 mysteries. And I'm also going to orient it from the perspective of what you might call minimalism, or, a very conservative take on physics, okay? Which is, instead of like really speculating about 15 dimensions, whatever, we're going to ask a question, some real physics questions here. And one big question that we are still, that there are many levels in astrophysics that we try to understand is what is the origin of cosmic structure? I'll say a little bit more about that. So, what is the physics that gives rise, right, to the origin of cosmic structure in all its glory? We know that dark matter exists. We have many probes, a handful of probes to know that it does exist and we need it. But what is its character? What is its identity? And how is it related to the visible things in our universe and also the laws that reign in the visible side of our universe? And the other mystery is, why is there more matter over antimatter? So even though if you look at the structure of we'll talk about the standard model, there should be an equal amount of matter and antimatter. And so why do we see way more matter and antimatter? And the point I'm going to make today, or an orientation that I'm going to make, is that maybe we can entertain the question that maybe these three mysteries point to a common cause. What do I mean by that? So let's get into this a little bit more. What do we know? So instead of what do we know is true in terms of physics? Well, we know in terms of gravity, the gravitational interaction, that Einstein's theory of general relativity has made predictions that have all come to pass. It predicted the existence of gravitational waves that even Einstein himself thought would be too faint to ever detect, and that has been detected by LIGO. Nobel Prizes have been given. Black holes is another example, right? So the expanding universe is another prediction of GR, and of course the solar system tests that we can see, the perihelion of Mercury. So we believe that the correct theory of gravity, at least classically, is general relativity. Another thing we know is that the three other interactions is governed by what we call a standard model of particle physics. Okay, so these are the things that we do know, and I'm not saying that these theories are not limited, but the standard model is a quantum field theory, it's a quantum theory, right? And general relativity is a classical theory. So we can ask the question, well, what do these theories share in common? Okay, so, if we wanted to kind of get a sense of the anatomy of these theories, the things that we know, how do we, what's underlying these theories? Is there something they have in common? And it was Albert Einstein that helped us understand that there is something that they all have in common, even though they appear to operate in different regimes, in different realms. GR, general relativity and the standard model. What is it? What is the principle? Well, in both cases, that principle is a principle of symmetry or invariance. The idea that if I change a physical system in different ways, I perform symmetry transformations on the system, right? There are, that those laws are the things that remain invariant, that remain unchanged. Okay, so the standard model and general relativity both enjoy symmetry principles, and so it's at that level that they're both similar, even though they operate in different regimes. However, they differ in one crucial way. And they differ because the standard model is what we call chiral, and general relativity is not chiral. So the idea here is that my strategy in this talk is to say, let's talk about what we know, let's see what they have in common, and let's see where there's a rub, and let's try to address that and see if we can address these three mysteries by making one of these theories accommodate the principles of the other theory. So GR is not chiral, and the standard model is chiral. What do I mean by chirality? What do I mean by chirality? So this picture is meant to give you an illustration of what is chirality. So let's consider on the left-hand side, this blue thing is supposed to be some kind of a mirror. Let's only focus on the left-handed side here. On the left-handed side here, we see this thing called WL. That is, think about that as some kind of interaction, right? That's something like, you can think of that as a photon. But what it really is a W boson, which has similar properties as a photon. It's a charge carrier, right? It mediates an interaction. And what that interaction is mediating, we see a left-handed spinning, so we have something that's spinning, right? So this W boson has like some kind of circular polarization. It's spinning to the left. And we have basically an electron and a neutrino and an up quark and a down quark. And what we see is that when the up quark, this up quark transmutes into a down quark, it emits a left spinning W boson and then creates an electron and a neutrino. And this interaction is what we call beta decay. Okay, this is something that the weak interaction has, and all decay products usually obey this basic interaction, which is the interaction that tells me how a neutron transmutes into a proton. But the key takeaway here is that all of the states, all of the particles there are all left-handed. So the essence of chirality is that left-handed interactions couple only to left-handed interactions, and right-handed interactions know only about right-handed interactions. So a chiral theory, right, knows about the handedness. The interactions distinguish between the handedness of the basic interactions. Now, there's a deep connection between chirality and parity, meaning if I look at the mirror reflection of a chiral interaction, the left-handed chiral states will swap into right-handed chiral states. And so not only is the standard model of the weak interaction chiral, meaning that it can distinguish between left-handed and right-handed states, but it's also parity violated, meaning that the mirror image is never seen in nature. Okay, so that's a connection between chirality and parity. So the standard model has this property. General relativity does not have this property. General relativity, unlike the W boson, produces something called a graviton, or its classical counterpart of gravitational waves. And gravitational waves actually cannot distinguish. It will produce just as much left-handed circularly polarized gravitational waves in a basic gravitational interaction as much as right-handed. So general relativity is achiral in that sense. Now let's get to the problem of large-scale structure. And so now what we're going to try to do now is to ask the following question. Imagine that we can make general relativity chiral. What would it gain for us? What would it buy for us? Would it help us understand these three mysteries? So let's talk about the first mystery, and that's the issue of structure formation. This is a picture of the Planck data, which looks back at the early universe when it was very hot and dense and dominated by a fluid plasma, something that Elon studies in her PhD, a plasma of super fundamental particles oscillating with an energy, and these oscillations are very tiny, and they grow into our analysis of this data. We know that this grows into these tiny perturbations, so-called density fluctuations of the CMB, grow into galaxies and systems of stars, which are galaxies, and the plethora of large-scale structure. And so I'll get back to that. And so if we look now at this sort of Fourier transformer, we look at the wave representation, the oscillations, we see this beautiful agreement, best fit of the CMB fluctuations. And it does reveal that the properties that we see back then, some 300,000 years after the Big Bang, does agree with a large-scale structure, provided that we have dark energy and something called dark matter and dark energy. Obviously not going to talk about those mysteries today. They deserve a talk in and of its own. And maybe in the future, you should invite Dr. Cyril Krex-Sarbonowski, who's at the CCA, to talk about that stuff. So, but we can ask the question about large-scale structure. When you look back at the early universe, it still had stuff there. I mean, by that point, you had electrons and you had photons, right? And you can ask yourself the question, where did those electrons come from? at an earlier stage. Like, if you go to the moment of the Big Bang, we can ask, well, what, how did that all happen? And we believe our fundamental paradigm our paradigm is something called cosmic inflation. At earlier times, going even maybe back to the Planck epoch, maybe what's going on that generates that is that the universe was dominated by a field stuck in its vacuum, in a false vacuum called the inflaton field, and the energy stored in that field, according to Einstein's theory, would create a rapid accelerated expansion of space, taking a tiny universe and making it this large macroscopic universe. And that's a picture of this inflaton field rolling down, and as it rolls down, it creates this rapid expansion. And this picture is supposed to say that you get a free lunch, actually, with inflation. Because not only is inflation making, the universe large, but what inflation does is that it predicts quantum fluctuations of this inflaton field. So this inflaton field, in its vacuum state, undergoes quantum undulations, and the rapid expanding background, in a sense, sources and drives these quantum fluctuations to become large and classical. And the energy density stored in these quantum fluctuations that now become classical end up sourcing the gravitational potential to actually induce the first imprints of these fluctuations that we see in the CMB. So we believe that, in a much earlier time, it's this phase of vacuum domination of the early universe and the quantum fluctuations that we basically, if you believe the story, we all arise from these quantum fluctuations. But if that was the story, it'll all be done. But for those of us that know a little bit about any kind of quantum fluctuation, about quantum field theory, we know that if you're going to get these quantum fluctuations, you're going to create matter and antimatter. And if we rely now on the standard model to actually, of the particle, the zoo of particles in the standard model and the interactions we know about in the standard model, I told you that the standard model, right, predicts just as much matter as you should have antimatter, at least at those very high energies. There's a caveat. The weak interaction could have processes that would violate the statement, but at very, very high energies that we believe inflation is happening at, for example, at the grand unified scale, 10 to the 16 giga electron volts versus 10 to the 3 giga electron volts for the weak interaction, there should be as much matter as antimatter, and the action of inflation, the quantum fluctuations will just source an equal amount of matter produced from this quantum vacuum as antimatter. They will meet each other and they will annihilate, and you would not have the density perturbations that we see. And this is the third mystery, and that mystery is basically baryogenesis. So there's another word for the matter-antimatter asymmetry. We call it baryogenesis if you're producing baryons. But there's another version of this. It's called leptogenesis if you want to produce more electrons or leptons or neutrinos. Either way, they're both interrelated. So if I can explain leptogenesis or baryogenesis, I explain the other. So I'm now segueing and I'm connecting the issue of structure formation, and the fact that if we rely on something like inflation to do structure formation, we have to now deal with why should we, how do we actually bias? Should we produce more matter and antimatter? So that's now the second mystery. And what I'm saying is that the standard model is not enough to do that. There are versions, again, of leptogenesis where you have to introduce some new physics. What I am focusing now is that the idea and the possibility that leptogenesis or baryogenesis can work with inflation to produce the imprints of structure formation, which is the density perturbation, and at the same time produce more matter over antimatter. That's the take I'm going to make in my talk. So what do we know about leptogenesis? The statement is that the universe is dominated with matter over antimatter. And the cosmic microwave background, my colleague David Spergel, along with the WMAP collaboration, they measured actually, they can count the number of baryons actually in the CMB, and they can measure that to be, so what they're really measuring is the number of baryons over antibaryons divided by the number of photons, basically. So that's this thing called the baryon asymmetry index. It's a very important number. It is the one parameter that controls something called nucleosynthesis. So if this number differs by away from this fine-tuned 10 to the minus 10, we have a hard time reconciling nucleosynthesis that we see in galaxies. So if you look at this number, all right, we need to explain this number. It's not just we need to explain that why there should be more baryon over antibaryons, but also that why this number, okay? And so what do we need to get baryogenesis or leptogenesis? Well, we need to explain this number, but in 1967, the Nobel Peace Prize winner, Andrei Sakharov, said we need 3 conditions to happen all at the same time. We need processes that go beyond the standard model that violate baryon or lepton violations. So you remember in the standard model, those currents, the currents that produce baryon number are vanishing, the divergences of those currents are vanishing due to Noether's theorem. CP, we need basically to bias. So imagine I have a situation where I can accomplish violating baryon number, the baryon number production in the early universe. Or if I don't bias, if I don't produce baryon over antibaryons, I'm just going to produce baryons and antibaryons at the same rate. So we need to bias that with something called charge conjugation and parity violation. Just like the weak interaction had that parity violation, I need to bias the first condition by CP violation, and this has to happen outside of equilibrium. So remember, the universe is expanding. So what you need is basically these processes to happen slower than the expansion rate of the universe. So now, what I'm going to now move into now is to say, so I want to make the statement that we need new physics. The standard model and GR as we know it is not enough to explain this in the context of the models of inflation that we had worked on. And we rely on the model of inflation to understand the origin of structure in the universe. So we need to do something maybe to make inflation be equipped with the characteristics to do baryogenesis, and therefore in so doing, it may address the issue, this particular issue of large-scale structure. And so one way we want to do this is, let me just back up for a second and say one of the things that come for free. So again, this is the minimalist in me, and to say that one of the things that come for free is that gravitational waves are produced necessarily during inflation. So that we're going to keep that in the back of our heads as we are moving forward, which is that during inflation, you cannot avoid the productions of the ripples of space-time during inflation. And because of that, we're going to make use of that fact moving forward. So what we're looking at here is a wave equation, although the middle term shows that it's a damped oscillator, or actually an overdamped oscillator, for a given Fourier mode of a gravitational wave during inflation, and A is the expansion rate of the universe. And the point here is that inflation produces a spectrum of gravitational waves that actually get amplified and become squeezed and classical by the end of inflation. And we're going to make use of this. But take note that what inflation is going to do, if we don't modify general relativity, is it's going to produce an equal amount of left-handed gravitational waves and an equal amount of right-handed gravitational waves. What we want to do is to figure out how to get around that. Right? And the reason why is that if you can do such a thing, then maybe you can equip general relativity actually to be closer to the standard model and actually to have chirality and also parity violation. So what is this? Now, what we're going to now do is actually make gravity chiral. How do we do that? Let's get to the next slide. So moving forward, I will show some equations. And all I really wanted to show you here, all right, the thing I'm going to focus on is the bottom box here. And to make you to just get you to realize that the top equation is an action principle. It's an action. It contains the Einstein-Hilbert term, the term that all the way to the left that says kappa times r. That is the Ricci scalar. And then we add now some extra structure to general relativity that's going to make general relativity chiral. And what we see here, we have something that goes as the square of the curvature. And then we have all the way to the right this thing called theta. It's a field. It's like a scalar field, a spin zero field. And this field actually, that's a kinetic term for that field, kinetic energy. And if you look at now the modified equations of motion, like the same way we look at like Maxwell's equations, this is an equation that governs the curvature of space in the presence of matter. We see that it'll differ from general relativity in this very interesting way. And the way we can see that it differs is to actually go back and look at the perturbations of space-time. Look at what a gravitational wave looks like in the presence of this theory. And so in ordinary general relativity, what we see is that the wave equation for the left-handed gravitational waves, if it was just ordinary GR with these two extra terms to the right here upstairs, if we didn't have those two terms, we would see that what I call box H left and box H right. Box just means a wave operator, right? H left double docked minus the gradient square of H left. In other words, if I didn't have these terms, it'll just be box H left is equal to 0 and box H right is equal to 0, which corresponds to a gravitational waves propagating in vacuum. A gravitational waves propagating in empty space-time. But what we see here is that when we turn on these extra terms, something fantastic happens. You see, what we see is that the equation for the left-handed gravitational wave is equal and opposite to the equation for the right-handed gravitational wave. They differ by a plus sign and a minus sign. And so if we look at generic solutions of this gravitational wave, what we see at the end of the day is that the left-handed wave will actually attenuate or die off, and its energy will flow into a right-handed gravitational wave, which will get amplified. And that is what we now mean by chirality, because the left-handed gravitational waves now will couple to left-handed matter species, and the right-handed gravitational wave will couple to right-handed gravitational species. But because the right-handed one is growing and the left-handed one, its amplitude is dying, we're also going to get parity violation in general relativity. This theory is known as Chern-Simons modified general relativity, and it was something that that was pushed and studied many years ago by me and my graduate student back in 2005. And I guess it made the Simons Foundation happy, and they have funded further research on this project. But the point is that, what are the consequences of this? So this theory is known as Chern-Simons gravity. It is a chiral theory of gravity. It is the only way we know how to make general relativity chiral in 4 dimensions without any problems, like literally theoretical problems that you run into, like having ghost-like instabilities and all these other problems that I want to talk about. But it's right now the only way we know in 4 dimensions how to minimally make general relativity chiral. And the other thing that's interesting about this theory is that it finds itself at home in many approaches to quantum gravity, including string theory. So it comes about actually when we start looking at corrections to gravity in the quantum realm. So now we're going to revisit the story of baryogenesis and hence structure formation by making gravity chiral, by making it resemble more of the properties that the Standard Model has. I already said that. I already said that. And so before I, talk about any more details, I kind of want to spell out how this thing works. So what we're going to show is that during inflation, when gravitational waves are already inevitable, if it is governed by chiral gravity, if it is governed by this Chern-Simons theory, and not by ordinary GR, can I generate the net baryon asymmetry just from making that one change? Everything else remains the same about the standard model. Everything else remains the same about inflation. And the answer is yes. And it turns out that, again, there are many approaches, not many, but there are a handful of, viable approaches to generating the matter asymmetry in the universe. But this one is special in that all of these Sakharov conditions happen from one and only one thing. And the idea here is, if you look at this triangle, it's really the minute you actually have inflation happening, right? The inflaton field will couple or interact with this scalar field that's coupling to Chern-Simons gravity. So let me just go back here. You see the state of field here. The inflaton field can communicate with this field in a way that it will source H left and H right to be biased. So if it does that, the onset of inflation, right, will source these gravitational waves where there's an imbalance of the left-handed amplitude of the gravitational wave and a right-handed amplitude. And that is actually parity violation. That is a form of CP violation. So that's one of the Sakharov conditions. But the minute you actually, you're doing that, remember, inflation is happening so rapidly, the expansion, that process of CP violation is already out of equilibrium. Now all that is left to do is to show how the CP violation is related to the lepton number production, the third Sakharov condition. And now I'm going to show you how that works, and it's quite remarkable. So the minute you produce these gravitational waves, and they are biased, and you have more left-handed and right-handed, you now immediately get the following. So forget about these indices. That is not necessary to understand what's going on here. What you should look at on the left-hand side is you want to think about something called a continuity equation. The continuity equation tells me, what is the rate of the production of the number density of a quantity? In this case, J mu is just, in some approximation, the number density of baryons and leptons from the vacuum. And the right-hand side is related now to the amount of left and right-handed gravitational waves. And what this equation, this is something called a quantum anomaly. And actually, one of the Nobel Prize winners, Abdus Salam and his collaborators, and these other authors, show that the standard model actually has a gravitational anomaly. What do I mean by that? That if you have enough left versus right-handed gravitational waves, you can actually anomalously produce more leptons over baryons. So how would I do such a thing? So what we need is the right-hand side of this source to be non-vanishing in a very particular way. And the answer is, we get a drum roll. The answer is that it's exactly the amount of left versus the net amount of right versus left-handed gravitational waves produced during inflation by the action of chiral gravity. But the minute I do that, I will generate a non-vanishing right-hand side for free. And if you now take those solutions and plug and chug, there it goes. You can now calculate the number of baryons divided by the number of photons. And that you find is that if you now look at the observational constraints of the scale of inflation, which is h over m Planck, we know that's roughly 10 to the minus 5. If, for certain parameters of the amplitude of 10 to the scalar ratio, and then this one parameter, which is the cutoff scale of our theory, and within a very good range of valid effective field theories, we can actually accommodate the correct amount of baryon asymmetry. So the nutshell is, for free, if you believe in inflation and you believe that chiral gravity is functioning during inflation as the correct theory of gravity, the net production of gravitational waves will generate, along with inflation, the correct amount of Sakharov conditions and the correct amount of baryon asymmetry. And so this is recent work by my colleagues, Pete Adsheads and Rob Caldwell and his colleagues, and others that actually show that there are actually predictions for upcoming CMB experiments that could actually constrain such processes. So it's not just, pie in the sky kind of theoretical dreaming. There are real observational constraints that we can go and measure in future CMB experiments. And how am I doing with time?
I think now would be a pretty reasonable place to stop so that we have around 10 to 15 minutes for questions.
Yes, so I want to end now with saying that the action now is in our own backyard, where we can look now at the effect of this chiral gravity theory with binary objects. So here are some authors and some work. I want to pay attention to some most recent work by my former PhD student, Leah Jenks, and myself with Greg Gabadotze and Nico Younes, where we've been looking at rotating black holes, realistic rotating black holes, and the effect of chiral gravity of dynamical Chern-Simons theory. And maybe you could invite Leah in the future to give a talk. And given that, I will now end my talk. Thank you so much for your time. So all this other stuff. It's a dark matter story to tell you.
Thank you, Dr. Alexander, for a really, really exciting talk. It was very interesting. So at this point, I want to open the floor to questions. If you have a question, please feel free to leave it in the Q&A, using the Q&A feature at the bottom panel.
So maybe we could, should I keep the slides on, or should we just get back onto a regular screen?
I think if you keep the slides up, that may be useful in case.
Yeah, I can read, yeah, go back to the thing, okay.
I did have a question of my own,
Sure.
and it pertained to the slide in which you introduced chirality, and you'd made the statement that you can classify interactions as chiral, but I had a question on how do you classify the main particles as how do you classify the chirality of the main particles, because it's very intuitive how you can classify the chirality of the interaction particle, but I'm a bit confused on the chirality of the up quark and the neutrino.
Well, that's an excellent question, Paulton. That's a great question. Fantastic question. Okay, let's get into this. So, it's really interesting. You learn in special relativity, there are these things called the Lorentz transformation, right? And when we think about the Lorentz transformation, we are informed that we can look at a 4 vector, and we can rotate this 4 vector from a space-like coordinate to a time-like coordinate, for example, because it's a 4-dimensional space-time continuum. It turns out that, very interestingly, there are other types of special vectors that are also representations of the Lorentz group as well, and they're called spinors. And what happens is that there's a spinorial representation that Paul Dirac taught us, and they come in a left and a right-handed representation. Meaning that if I rotate them using the Lorentz transformations, they retain their left-handedness under the Lorentz transform. And those spinors are called chiral spinors. So it's actually it's actually related, the handedness of the electron and the quarks. These things are really just, the irreducible representations of the Lorentz group. It's a very beautiful and deep piece of mathematics that's connected to special relativity. So thanks for asking that question.
So they're not actually a quantum property. They actually arise from classical physics.
Ooh, that's a very good question too. Well, they are, we're taught by Wigner that, so very good. they become quantum, actually. So they start off as a classical thing, but then we are told that that chirality becomes a current a quantum number, right? So we can turn it into a charge, actually. And when we can turn a classical charge, we have a classical charge, we are informed when we quantize that charge can be quantized. So therefore we can quantize a chiral charge, and the anomaly is an example of actually the breakdown of that quantization of charge. And luckily the standard model fixes that problem as well. So anyway, these are all very deep questions that you're asking.
So it looks like we have a question. So one of the participants asks, our participant actually is Alan Pierre Lewis, who is another member of the student council. He asks if you know of any experimental apparatuses that can help probe Chern-Simons theory as it relates to QCD, and what energies would be needed for such tests.
That's another excellent question. So recently there are papers using, I guess, nuclear spin, and I think this is I forget the gentleman's name, but I'll share that. But they can use the fact that that's right. So axion, which is related to this chiral gravity, does actually couple to QC the strong interaction, although it's a different type of axion. It turns out if this axion oscillates, then it will change the nuclear dipole moment in a very, very faint way. So you'll need very controlled and sensitive experiments, like, I forget exactly what types of experiments, to go and probe actually that effect. So basically, in a nutshell, the axion could induce a very tiny electric dipole moment for a neutron, and that thing could actually, potentially be probed with very sensitive experiments. But the experiments that we use are actually spinning black holes, for example.
Thank you for answering the question very eloquently. So I think I had another question, and it relates to, I guess, very much the same. If there aren't any, there are experimental apparatuses that you theorize could probe like Chern-Simons theory to explain baryogenesis with gravity and inflation. Do you expect to see any like astronomical observations or do you expect to explain any astronomical observations with Chern-Simons in chiral gravity?
Yeah, so my former student Nico Yunez and other collaborators, Leah, have been working on their own ways of looking into this. One of the things that we're working on now, a paper soon to be released by Cyril Krex-Sarbanowski, who is an NSVP member, Mark Kamiakowski, myself, and Oliver Philcox. We're actually looking at the possibility that galaxies themselves, if you look at now the distribution of galaxies, there might be a way of probing, but with something called a trispectrum, which is basically like a 4-point, like a correlator that looks at tetrahedral like configurations of galaxies to look for parity violation in galaxies and connecting that to Chern-Simons gravity. And that paper should be coming out soon. We're still trying to understand that stuff.
Okay, this is, we don't have any other questions in the chat, but I think I'm going to pass it off to our president, student council president, Elon, to start wrapping us up.
Thank you, Carlton.
Thank you.
Yes, thanks, Carlton. Can you guys hear me well?
I can hear you.
Okay, awesome. So I just want to go ahead and thank again our speaker for this month's Innovate seminars, Dr. Alexander. I appreciate you coming here and gracing us with your presence. And I appreciate your
Thank you.
service to the National Society of Black Physicists, specifically the Student Council, in helping us to create this vision for the series, and also for your partnership that you created with KITP.
Thank you. And we thank the KITP for their continued support of NSVP.
Yeah. So with that, I'm going to close out this month's Innovate. Next month's Innovate, stay tuned because we will be featuring the winner of either the oral or poster presentation at this year's annual conference.
Can't wait.
So that's going to be at some point at the end of November. So I hope everyone has an excellent Thursday. And if you're watching the recording of this, I hope you enjoyed. And happy Thursday. See you next time.